Okay, thank you for the introduction. The title is Active Learning in Efficient Estimation for Basin Stability of Dynamic Networks. So to begin with, the dynamic networks are a ubiquitous representation for human-made infrastructure systems like the power grid networks. And the interdependency between the components of the networks has rendered such systems susceptible to the cascading failure. Basically, small problems can usually give rise to large consequences, like the power grid networks, which is fragile. We know that it's very fragile, and interdependency between the nodes and the components. So particularly in recent years, of our past 2 decades, we have seen the penetration of the intermittent and the volatile wind and solar power into these grids, and which have given rise to the further problems for grid operation. And one case in point is 2 years ago in Texas, we have a power grid system problem. And another high-profile outage in Arizona back in 2011. And the problem was stemming from a large transmission line tripped out of service by mistake. And there is a phenomenon called power flow redistribution. So we have a power flow that passed on this line that was tripped out of service. And because of this, the power flow was redistributed to other nearby lines and giving rise to the overheating and further knock down those power lines. And eventually the failure cascaded out to the transportation network and the communication network. So overall, almost 3 million people lost power in California, Arizona, and Mexico. And so the motivation, we know that we want to see what kind of small errors can give us those large mistakes with a huge consequence. So we want to see whether instability or a cascading blackout in the grid. And we want to adopt novel models to help us preempt the potential failures. And so we can have a guidance information, how to design, how to control those networks. And one concept is called transient failure in the power grid system. So we want to describe the capability for network, when we have some perturbations from weather, from the mistake. After that, my network can converge to the equilibrium conditions. So in terms of the dynamic systems. So the stability means I want my network to go back after the transient period. That's from the perturbations. So if a perturbation only gives rise to the narrow angular departure, that's about the generator. I will go to the generator dynamics. And from the equilibrium of the generator dynamics, and my system can go back. That means the system is reliable or stable. And we know that we have Lyapunov function, the very fundamental function to evaluate the system stability. And it's cumbersome to formulate for some complicated equations or governing systems with governing equations. And particularly for a high-dimensional system, it's not easy to write out the Lyapunov function. And it only gives a low bound on the basin of attraction, the basin of attraction. So here the BOA is the ensemble of the states, and from which my system can eventually converge to the equilibrium conditions after a long transient period. And it relies on linearization of your system equation. And we use local approach. And so we cannot model a non-local effort, like we have a huge disruption from hurricane to the power grid system. So here is the concept for basin stability. We want to use basin stability to model such large-scale perturbations. And so you cannot rely on linearization anymore. This is a portrait for basin stability. We have a fixed point B here, and we have perturbation. So with this perturbation, your state will change from XA to XC. This is a picture from Manka in 2013. So within this basin of attraction, the BOA, my system can always go back to the fixed point B. That means my system is stable. We use the basin BOA volume to represent the probability or likelihood that your system can eventually go back after such transient period. I will use the Amazon rainforest, the Earth's most critical natural defense against climate change, to explain the basin stability. So we have the bistability for the system, the barren savanna state and the fertile forest state. We have the two stable states. And here we can use a very simple model, a one-dimensional system to represent the forest cover X. So with very large X, we have very large rainforest cover. So we can bring a lot more rainfall and improve the vegetation condition, and we can enhance the water balance. There is no problem for that. But on the other hand, with the destructive deforestation, so X will decrease. As X decrease, and the system was deprived tons of water, which is otherwise absorbed in the vegetation. Okay, so here the X is a critical forest cover threshold, indicative of the degree of dryness. As dryness increases, X will also increase. So you solve this system, you have two equilibrium, right? X1 equal to 1 minus d over S, that's for the forest state. And the other one, X2 equal to 0, that's the savanna state. Now, if you use the Lyapunov function, you solve the Lyapunov exponent, you have two, both are negative. So we have two fixed points. But those two Lyapunov exponents, they are independent of your Xc. Does not matter what's Xc, even the dryness condition increases. Xc increases a lot. You cannot see anything from the change for this Lyapunov exponent. There is no change, right? So we have no idea of the slowing down of recovery, okay, from the perturbation, And so here I plotted the BOA, the basin of attraction for this system. So here on x-axis, X will change from 0.3 to 1. So 100%, that means you have the 100% forest cover. And axis will change from 0 to 0.9, some value on the y-axis. You can see that as X increases, the BOA will shrink, right? The BOA will shrink. And you cannot get this idea from the Lyapunov exponent. So what can we define? How can we define the BOA change or the likelihood that my system will eventually go back? So that's the basin stability. It's actually a very simple concept. We have general dynamic system, X dot equal to Ft. You define initial condition, and you have the BOA, the basin of attraction. And we have also indicator function. Okay, if your X is within BOA, that means my system will eventually go back. That's equal to 1, otherwise it's 0. So the basin stability B is just the integration for this simple form. So rho X is the PDF for your state. I know the estimation for Xt or estimated distribution for the perturbation. Like I have this hurricane in Florida. So we estimate what kind of distribution I will have on my system state, on the power grid state X. So this B actually is between 0 and 1, quantify the probability, give you a probability. What's the likelihood your system will eventually go back? And in practice, we can call on the Monte Carlo simulation. I can generate a large number of X. And then I do this ratio, small n over capital N. Capital N is the total number of sampling points I have, and small n means those points will eventually go back. But we know that there is huge computational cost, right? Particularly if you have large, high-dimensional system and you have very complicated governing equations. So you need to spend a lot of time to do this simulation. And so here I plotted the basin stability. At left-hand side is the BOA. We see that X increases, or BOA will shrink. And on red panel, I show that the basin stability actually will decrease for a foreign state. I have two fixed points, and both of them has the basin stability. So as Xc increases, so the dryness increases, the basin stability will slowly decrease. You cannot get this information from the Lyapunov exponent. And then we want to use this basin stability to study the power grid networks. So we have N nodes, and we have Ng for a generator and N minus Ng for motors, or we call it load. That's basically consuming nodes. And at equilibrium points, the power supply and demand strike a balance. There is no problem. And that's called the synchronous state. All generators or motors, they run at a reference frequency, 50 or 60 hertz, depending on where you are in the world. That's a reference frequency. And so in the US, now we focus more on N-1 reliability. That means I will perturb one of the nodes. And I will see which node is the weakest. That means I need to do the enhancement. Before the hurricane comes, I study this. I know the N-1 reliability, which is the weakest point I need to enhance against nature. So here is a model for this network dynamics. For the generators, we use the second order Kuramoto model. So theta and omega, they are the two elements of X in my previous slide. They are the states. So theta is a rotational phase angle for the generator, and omega is the angular frequency. Okay, angular frequency. And the Pi and Di, they are the power and also the power demand, and the power divided by the generator and also power demand from the consumer nodes. And they are connected by this Di. So as demand, actually, we have a weighted agency matrix, Kij. Okay? If there is no connectivity, Kij equal to 0. Otherwise, it depends on the power line that connects node I and node J. And also, we have dynamics on the load, and then we put them into the power grid networks. This is the model that describes how the power grid networks will evolve as time changes. So in equilibrium condition, Pi equal to Di, there is no problem. Okay, that's the equilibrium state for your power grid networks. And we have synchronous state of the grid. That's all omega, they are the same. Okay, that's the reference frequency around the world. In different countries, we have different value. So we follow the convention in the literature from IEEE. So we rescale theta I, Wi with respect to theta I star. That's the reference value for the angle for each generator. Okay, so each generator has its own reference value for the theta, and the omega is the same. Okay, it's the same in the US. So, and we rescaled, so that means 0, 0 is my equilibrium state. Okay, so eventually I want all my generators converged to this 0, 0. So that means there is no problem. Again, now we studied n-1 reliability. I want to perturb each node, and the PDF can be estimated from using our historical experience or historical data. So now only one generator I is perturbed, and the rest node will stay the same. Okay, for the initial condition, but eventually it will be affected by this perturbation, right? Because it's networked system. Now these are our initial condition. Every node we start from 0, 0. That's the rescaled equilibrium condition. And for node I, there is change for the angle and the frequency and angular frequency. So the idea is that can we use machine learning to accelerate this simulation? Now, if you have n nodes in reality and maybe over 1,000, and the system is too large to solve in a short time period, and so the idea is that can we use machine learning to accelerate this? I want to make a simulation fast. Okay? So Basin stability is a binary classification problem, right? I have a node and each point or the perturbation value, and I want to put it into stable or unstable classes. So I have two classes, two labels I want to put, and it highly depends on the training data. Okay. So how do you want to select training data that you can efficiently learn the basin of attraction or the basin stability? So we use the active learning idea here. I want to sequentially select the most informative design points. Okay, those points are realization from the perturbations. And so for the classifier, we use a relevance vector machine, and which was proposed almost 20 years, more than 20 years ago. It's a probabilistic classification model. We have the predictive uncertainty. So I will not only give you a label as in SVM, spot vector machine, but I also give you a probability. So it also favors the sparsity. Okay, the sparsity which will improve the computational efficiency. I will not talk details about this classification model, and this is the output. Okay. I have my y is a label. I have 1 or 0, stable or not. And given the x and one realization from the perturbation, I want to study label. Now, this probability is within this interval. Okay, sigma is a logistic link function. So whenever I have x, I know this is a prediction. Okay, and v is a variance from this model. Now, here is my learning algorithm. I have the training data set, xt, yt. That means I will take these samples for perturbation, and I run my system. Okay, I have n nodes. Each node I have the Kuramoto model, and I know what's the label, so I put yt. So that's my training data. I do not want to do simulation for a large number of data points. I cannot afford the computational cost. And I have unlabeled xu. I know this kind of perturbation, but I don't know the label. I don't know whether it's stable or not, and I want to get the idea from this active learning. You only use a subset of those points. So now that's the most informative data point, small xu, belongs to your unlabeled pool. But how can you pick them up? Okay. So when I pick up this small subset, I will do the simulation on only this small subset, and then I put a label. I can update my boundary and update the predictive model. I will do this sequentially until the boundary will converge. Okay. My hope is that by doing this, I only need maybe 20% of your original computational power, even less. But there is a near duplicate issue in this informative point selection. That means theoretically, I want to select points, okay? Given x, the probability equal to 1 is 0.5. That means it's on the boundary, almost on the boundary, right? Or you can do a probability. 0.5 belongs to this interval. That's the prediction probability. But if you just do this, you have the issue of we call the near duplicates. That means the points are very close to each other, right? They are close to the boundary, but they do not give you more information about what kind of boundary you will lack. This is called the near duplicates. That means you focus too much on the local behavior, and you forget about the global behavior. You do not do a good global exploration. So these slides explain the near duplicates in my another piece of recent work. So the left panel I have this near duplicates. The black contour are my target function in reliability engineering. I want to know what kind of area my inside structure is stable, outside is not reliable. Okay, I want to approximate this boundary. And of course, you have to do a lot of the simulation points from x1 and x2 to do that. And the blue line are my initial training points. So I do simulation on those blue points, and I get I know the outcome. And next, I need to take the informative subset. If you just follow the procedure in the previous slide, the probability is very close to 0.5, and you get a cluster of these green points. That's near duplicates. Each of them are informative, right? They tell you, okay, your boundary on that part is very close to those green points. But collectively, there is no information, right? Collectively, there is no information. The right-hand side is my another algorithm, okay? I do the diversity, I kind of spread out those points. Each of them are informative, they are close to the boundary. And together, they are also informative. They tell me, overall, what's the kind of contour shape you will lack. So that's the idea here. We want to avoid the near duplicates. My points, selected the subsets of the points are informative individually and also collectively. So to solve these, we borrow an idea from the operations research. There is a problem called the location analysis. Basically, you want to do the minimax facility location problem. You want to open up a number K of locations, okay? Locations for your facility. And such that the minimum distance between your new facility and all customers are maximized. So here in this metaphor, the customers are my training points. The new facility will be the new subset of informative points. So I do this to spread out my informative points so I can get the best idea of this contour. Okay, so now I do this simulation. First, we do a two-node network. We want to compare results to the literature. So I only have one generator and one load, a very simple system, okay? Only one edge network. And so we want to study the coupling strings K. K is the connectivity between this load and generator. So I have very simple Kuramoto model. And the coupling strings here for simulation, we put it as 1.15. And now I just assume uniform distribution, okay? Just assume uniform distribution on the perturbation on the theta and omega. And you can do the 4-factorial design. I have 200 by 200. That means I need to do simulation on 40,000 nodes, right? Those 40,000 nodes are possible values from your perturbation. So here, the black shaded area, that's the contour for the BOA, Basin of attraction. That means your perturbation within this black area, they are stable. The system will eventually go back to equilibrium. The network, there is no problem. But otherwise, in the white area, the system will totally be out of control. You may have the cascading failure on the power grid network. And so the black contour are from our algorithm. Okay, every time we select those like the green points here, those are my informative points, and I will estimate the contour from those green points, and I will update the boundary and update the prediction model. So eventually, after 37 steps, this is my estimated model. Okay, so I only use 1,260 current points, and I can estimate the BOE, the basin of attraction from a 4-factorial design. That's with 40,000 evaluations. And here we compare as we increase K, and what will be the basin stability like. So these are some conclusion from the literature, and we can verify that quickly with only small, slightly above 1,000 data points. So that means you need to enhance K, right? Whenever K is enhanced, you will increase the system reliability, but there is cost, of course. So you do not want to enhance every single line. You want to select the weakest point to do your enhancement before the hurricane, before other extreme weather conditions. And then we want to study the network. So here I use the IEEE 118 bus network. I have 118 nodes, and some of them are generators, and some of them are the consuming nodes. They will take power from the grid. And so as illustrated here, the green one are the generator, and the red one are the consumer nodes. We call it the loads. And I use different color to represent the connectivity. So you know some generators, they are very important. They connected to a lot of generators. Consumer nodes. And again, I want to study the N-1 reliability. I only perturb one of those generators, and I want to see the basin stability for the whole network, and see which one is the weakest. So here I explain the unstable and the stable, or the non-synchronous and the synchronous behaviors. So for the first left panel, I give perturbation to the W. I just pick up one single node. I do this perturbation. I want to study the N-1 reliability. And you can see here, after the perturbation, after this transition period, and my system quickly go to 0. That's my scaled reference point, is 0. Every generator will give you 0 value. That's good. And on the red panel, after this perturbation, my system does not come back. Okay, does not come back. So there is cascading failure, and the generator may eventually be burned, so be out of the system. So here I use a similar idea to sequentially approximate these contour. After you estimate contour, you can easily calculate the basin stability. So I use I choose 3 different steps, and eventually we have these contour estimation, okay, with only a fraction of all the training points. And so here I just label for all generators, I compare them, see which one has the smallest basin stability. That means you need to direct your resources to here to do your enhancement. So original simulation time was 8 days for Monte Carlo simulation for this IEEE 118 network. So you will use our algorithm. It only took 2.5 hours. That's how we use active learning to solve this problem. A summary: we use a classification relevance vector machine to solve this basin stability problem. So by nature, it's a classification problem, and we designed a sequential batch sampling to sequentially select the most informative subset of training points to update your system, to update the stability and also the predictive model. And we can estimate the network basin stability. And this paper is currently available in CHAOSS. Thank you for your listening.